Okay, this is the lecture video for MAC 1114, Trigonometry. We're in section 9.1, where we're going to be taking a look at the polar system, how to specifically plot polar coordinates, r and theta, and how that relates to rectangular coordinates, x and y, and then certain applications, also coming up with polar equations. So we begin just by taking a look at something that you've been used to plotting a lot coming up to this point, and that's plotting rectangular coordinates, where the x-axis, the horizontal axis, is for the first coordinate, and the vertical axis, the y-axis, is for the second coordinate, both real, real numbers. And then you've also had some experience with this in your previous algebra courses where you would plot a complex number. And in that particular case, the x-axis was where the real numbers are, so you would plot this portion, and then the imaginary coordinate would be plotted along this y-axis. So in this case, when you were plotting complex numbers, this y-axis would just take on a new role, and that would be to plot the imaginary portion of your complex number. Now we move into the polar coordinate system, and in these kind of points, the first coordinate is going to be r, which is just the length of this ray. I mean, it will be referred to as a vector later on in the chapter, but it's just the length. And what it's been for you throughout all these chapters leading up to chapter 9 is it has just simply been the rotating arm, which ended up playing the role of the hypotenuse. And so we could use Pythagorean theorem to relate y, x, and r. This would be the hypotenuse, this would be a leg, and this would be a leg. And you're going to see that we're still going to be relating r to x and y in that form. But when you're plotting a polar point, the first coordinate is r, which is the length of this, and then the back coordinate is theta. We refer to that as the direction angle. And when you plot these points, you're always going to start off by rotating to whatever the designated theta is, and then moving out a certain r distance. And I'm going to demonstrate that as we go on. When you're in the polar coordinate system, the x-axis is now called the polar axis instead of the x-axis. But you can superimpose one on the other, and instead of this being called the origin, it is called the pole. This axis is called the axis where theta, we refer to this axis as theta equal to pi over 2. And that's because to get to the y-axis, you have to rotate 90 degrees, and that's exactly what pi over 2 is. So this vertical axis is referred to as theta equal to pi over 2. Polar axis, and the origin is called the pole. And I repeated that information right here. Okay, so again, instead of x and y, you're going to have an r and a theta, and you're always going to rotate to the designated theta first, and then you will act out whatever the r value is, the r distance. We're going to bring back some formulas for you that were mentioned much earlier in the book. Let's see, they were first introduced in section 6.2, and we've been using them ever since. For instance, in section 6.2, we learned and have been using that cosine of theta is x over r. Let me write that a little bit better. Cosine of theta is equal to x over r. And that's exactly what this is right here. If you were to just cross multiply r times cosine of theta, just swing that r right up here, cross multiplying one way, you would have what you're seeing here. So this is equivalent to this. You were also given this in section 6.2 of this book, where sine of theta was defined as y over r. Once again, if you were to cross multiply r times sine of theta, that would swing the r right up alongside of the sine of theta, and it would be the multiplier, and it would look just like this. So these are just formulas from section 6.2, and they happen to be the definitions that we're going to use when we want to move from our polar information, r and theta, into the rectangular system. So in other words, by someone giving us an r value and a theta, if we go r multiplied by cosine of theta, we're going to get an x value. And if we use our r value times sine of theta, we can get a y value, thus being able to move back and forth between the polar system and the kind of coordinates that we see there and into the rectangular system where the kind of coordinates we see are x and y. This r squared equal to x squared plus y squared, that's nothing more than the Pythagorean theorem. Okay, you have a right triangle here. Hypotenuse squared is equal to leg squared plus leg squared. That's what that is right there. Tan of theta also introduced exactly as you see it here in section 6.2. And it is how we're going to be able to find our direction angle, but how we also relate our direction angle theta to y and x. Okay, I'm going to demonstrate all of these things, plotting and using the formulas to move back and forth between r and theta and x and y. Okay, so here you see just a place where you can go and plot your points. Notice that instead of having an XY grid, you have a graphing grid that looks like concentric circles. They are concentric circles, so a circle, then a bigger circle, then a bigger circle. And you're going to use these in order to plot these points. Now I've given you a little bit of each in these examples, in other words, negatives in different places so you can see how to deal with those negatives. But every point that you're being given here is in r theta form. So these are what we refer to as polar points. Again, you're always going to do this first. You're going to rotate to whatever the designated angle is. So I'm going to rotate in a positive fashion, which means I'm rotating counterclockwise. And I'm going to darken in that ray, and I'm going to move out a distance of r equal to 2. And when we say a distance of r equal to 2, those are counted using these ringlets right here. That's what I refer to them as. So here's 1, here's 2. Stay on that ray. That's rotated to 30 degrees, and right there that represents 2, 30. Where the 30 is your theta, and this is your r. Okay, if you are asked to take this information and relate it to the XY system rather than the polar system, because right now you're in polar coordinates, then you can use this formula right here. One reason that they always ask you to plot the polar point first is because they want you to see what quadrant you're in, because just because you have these concentric circles as your new graphing grid, you still have quadrants. You have quadrant 1. Right here is quadrant 1. You have quadrant 2 here, which is everything in here from 90 degrees to 180. You have quadrant 3, which is everything from 180 to 270. And you have quadrant 4, which is everything 270 back to 0. So we're obviously in quadrant 1. And when you go to find your x and y, that also must be in quadrant 1. So that's why you want to practice plotting the polar point first so that you can make sure and understand what quadrant you're in and use it as a checking point when you go to get your x and y value. It should also have the signs that force it to be in quadrant 1. In same quad as r theta. Okay, so let's go ahead and we're going to do our x value, and we're also going to do our y value. Okay, so when I plug into this, it's the r value. Our r value for part A was 2, so I'll put that right in there. and then it's cosine of whatever the theta is. So that's 30 degrees. You might want to draw a nice clean picture. I would suggest doing that. Rotate up to 30 degrees. Put that reference angle in there. And then drop down and complete your triangle. If this is 30, this would be 60 up here. Across from the 30 is always the short leg. Across from the 60 is the long leg. Hey, remember that vertical leg is always referred to as sine. It's related to the y value. Horizontal leg on your triangle is the cosine value. And this was all created by rotating our hypotenuse to 30 degrees, which is why this reference angle is 30 degrees. So that when you go to complete these values for x and y, excuse me, you can just grab the values right from the picture. So 2 cosine of 30, again, is just this horizontal leg. And then continue to simplify. This 2 right here, that was the r value, same thing as 2 over 1. That cancels with that, and you are left with just square root of 3 for your x value. Okay, now I'm going to get the y value, or once again, you can use this picture. You're just using a different formula. R is 2. And then we're doing sine at 30 degrees, and we've already drawn a picture of a triangle where the hypotenuse is rotated to 30 degrees, and therefore we can get both the sine and cosine off that picture. So it's 2. The sine is 1/2. This cancels with this, leaving you with 1. So then what you do is just collect these points together and report them as a rectangular point, the coordinates of a rectangular point. So here we're talking x and y. Notice that this point that we have right here, positive x, positive y, also is in quad 1. Okay, use that first picture that you've created by rotating to the theta and then moving out a certain number of units on that rotating arm, which is what you will always do if your r value is positive. So what this first example represented is how to plot that r value when it's positive. Notice that the next example I give you, you have a negative r value. So I wanted you to get some experience with how do you handle that situation. Again, you're always going to do, whoops, I left my S out right here. You're always going to do this first. You might want to think of it in degrees. Maybe that's easier to think of. So 2 times 180 divided by 3, that's a 120 degree rotation. So we're going to rotate to 120 degrees first, but we're going to handle the movement of the r distance differently, and that's because this is negative. Negative r value, we handle it differently. So rotate to 120, rotate here. This would be the arm that we're talking about right at 120. But when your r value is negative, you're going to move out a distance of r on the opposite ray. Whenever the r value is negative, you will do this. You're going to hop out a distance of r, not on the actual rotated ray, but on the opposite ray. Okay, so we're going to just take this and trace it back in the opposite direction. Okay, not going out 4 this way, but moving out 4 this way. So 1, 2, 3, we'll just approximate that the next one would be about right there, and that's where you plot the point. This would represent an R value of -4, and a theta of 120. Notice that you end up in quad 4 here. So therefore, when you go to figure out x and y, it better have signs that would put you in quad 4. Okay, so let's make sure. We'll check that before giving our final answer. Let's go at it. Okay, so here we have x is equal to the R value that they gave you for part B, which was -4, and the theta that they gave you was 120. So maybe we'll, draw a nice clean picture that doesn't have all of this on it to get so that we can visualize what the cosine and the sine value is at 120. Okay, so I'll just draw a little picture right here. I'm going to conserve space. Here I would be at 120. I would be rotated 120. I'd have to stop 60 degrees before getting to the 180 mark. This is the 180 mark when you get to pi right there, but you're only going to 120 with this rotating arm right here, which really plays the role of the hypotenuse. Drop down to the x-axis, realize you have a 60-degree reference angle. And therefore, this would be 30 degrees up here. Try to remember that the long leg, square root of 3 over 2, is always across from 60, and across from 30 is always the short leg. But because of the quadrant that you're in, you know that this horizontal leg represents the x value, or what we call the cosine. X values are negative in this quadrant. Okay, whereas this value that is on the vertical leg, that represents the sine or the y value, and y values are positive there. So this is negative, this one's positive. So when I go to do x and y, let me continue with x here. It's going to be -4. The cosine of 120 is just grabbed from the triangle that was created by rotating this hypotenuse to 120, leaving me with a 60-degree reference angle, a sine value of square root of 3 over 2, and a cosine value of -1/2. I need my cosine value, which is the value along that horizontal leg. So this is negative times negative is positive, and this is the same thing as 4 divided by 2. Okay, so there's my x value, and then since my picture is right there, I'm going to go ahead and do the y value right here. So y is equal to the r. Once again, my r value was -4, and then I'm going r times sine of theta to get my y value. This picture will serve to give us both the cosine at 120 and the sine at 120. The sine at 120 would just simply be the vertical leg. So -4 times square root of 3 over 2, which gives you actually just negative 4 divided by 2. This 4 divided by 2 is just going to be 2 with that square root of 3 hanging off the back. Okay, and that's your y. So you collect these together and you had a positive x but a negative y. Notice that this r theta that you plotted to begin with ended up in quad 4, and so did this. Your XY answer and your original R theta need to be in the same quadrant, or you have calculated something wrong. Okay, moving to C. And in C, we are plotting, let's see, 5 negative pi over 4. So here we were plotting 230. Let me just get a marker. Hold on one second. So in part A, we were just plotting 230. In this one, we messed around with the idea of what happens when your when your R value is negative, which made us, instead of hopping 4 units out on the rotated arm, we traced it in the opposite direction to deal with this negative R value. So that's what you're going to do if your R value is negative. Rotate to wherever they tell you to rotate, which was 120, but then trace it back in the opposite direction and move out that distance on the opposite ray. So that was for this case. And then in this third case, we are plotting 5, negative pi over 4 for part C. Okay, pi over 4 is 180 divided by 4. That is the same thing as negative 45 degrees, if you want to think of these in degrees. Okay, so if we rotate negatively, that just means we drop down instead of rotating counterclockwise. So 45 degrees, negative 45 degrees would be negative 30, and then another negative 15. That would put us right there. So that would represent a theta of negative 45 degrees. Okay. And then we're supposed to be moving out 5 units on that rotated arm. I'm going to actually move 5 units on the actual rotated arm because that R value is not negative. So you don't have to trace it backwards. So this will be out 1, out 2, out 3, out 4, out 5. And right there, once again, in quad 4, this would represent an R value of 5 and a theta value of negative 45 degrees. Okay, now we're going to move into the XY system. That answer that we get should also be in quadrant 4. So it's going to be x is equal to the R value that you were given times cosine of negative 45 degrees. And if you want to have a picture, a nice clean picture instead of this one, okay, here we go. Rotate down to negative 45 degrees. That still means, even if you're rotating to negative 45 degrees, that doesn't mean that the reference angle is negative. Reference angles are always positive. So there's my rotated hypotenuse down at 45, negative 45 degrees. That makes this leg square root of 2 over 2. But it's negative because this represents the y value, or what we refer to as the sine value. This is the cosine value, and in this, which is the x value. And in this quadrant, x's are positive while y's are negative. So when you're finishing this answer here, the picture represents this. You can get cosine or sine right off of that picture. So it's x is equal to 5. Cosine at negative 45 degrees is this positive square root of 2 over 2. Cosine is always the horizontal leg on your right triangle. And you can just maybe write this like this. And there's your x value. And then the y value, it's going to be the same, only negative. So the R value is 5, and then we want to do sine at negative 45 degrees, which just means we should be getting that sine value off of a picture that was created by rotating the hypotenuse to negative 45 degrees, which we do. This will give us both sine and cosine. So it's going to be 5, and then the sine at negative 45 degrees is square root of 2 over 2, negative. So you're going to get that same kind of answer, 5 square roots of 2 over 2, but with a negative. Okay, notice that a point, a rectangular point that has a positive x value and a negative y value is going to also put you in quad 4. Okay, so whole point of those 3 problems, learning how to plot polar points in the polar system, how to find their XY equivalents, and being able to be aware that both of those points, whether you graph them in the polar system or the rectangular system, must lie in the same quadrant. Okay, moving on to the next page. In example 2, we're doing something that was similar to what well, it's actually exactly the same as finding coterminal points. So in other words, you're going to plot a point that you're being given, 3, 140, and you're going to find names of other points that would cause you to land right in that same exact position as 3, 140. Okay, so in part A, it says give 3 other points. You just want to come up with other names of points that make you land right at 3, 140. This is R, this is theta. So first you should begin by plotting and seeing where it's at. And you don't need to draw those concentric circles. We're just going to rotate to 140. That would put you right here. You rotated this hypotenuse to 140, which means there's 40 degrees left over as your reference angle before getting all the way to pi or 180. And then you're moving out 1, 2, 3 notches on that ray, that rotating arm. So right here is where 3, 140. Now you want to come up with other names for this same exact point. I think possibly the most obvious one would be to make you land right on this same position is if you just rotated an additional 360 degrees. So why don't we give that as I'm going to give that as the first answer. Let's see. So one way to get another pair of polar coordinates that make you land right at 3, 140. Let's write this a little bit clearer. Is just to stand on the point you're at, rotate 360 degrees and make yourself land right back at that same position. Rotate an extra 360 degrees. What would the name of the point be at that point? Well, if you started off at 140 degrees and you added 360 to that, and you still wanted to be the same distance out on that rotating arm, you'd have to leave the R and then just go the 140 that you were at plus an additional 360, which would put you at 3,500. Okay, another answer that we can come up with that will make you land right on this same position, 3, 140, is if we rotate backwards. Instead of rotating this way, counterclockwise, we could rotate clockwise in a negative fashion. So rotate negatively. Do a negative rotation. Okay, so if I was going to rotate negatively, that means I would start at 0 and I'd want to rotate a negative 180 degrees plus an additional 40. So that would put me, if I'm rotating this time, going like this, and going negative 180, and then continuing until I get right there again, which would just be another 40 on top of the 180. So that would be 180 and another 40, rotating negatively to get a total of 220 degrees. So 3 negative 220 would put me right smack dab on that point. You'd rotate negative 220, you'd be right there, and then you would hop out a distance of 3 units on that rotated arm. Okay, you're just thinking of different ways to rotate to land right on that same point. Okay, one other thing that we could do is we could try a negative R value. We could rotate to the opposite ray. Then use an R value that's negative, which would cause you to land right back on this ray again. So this is what I mean by rotating to the opposite ray. So this ray was right here. It was, you had rotated 140 degrees, which put 40 degrees right in there as the reference angle. Well, if you were going to rotate to the opposite ray, that just means that it would be a continuation of this ray. Well, according to some of the geometry that you've learned, this and this are vertical angles. Those are called vertical angles. And vertical angles, they look like a little bow tie, and they are always equal. So let's say that you rotated to the opposite ray. That would have you rotating 40 degrees down this way. You'd be rotating negatively to negative 40 degrees, so that's going to be our theta. And instead of moving a distance of, let's see, what are we, a distance of 3, the R value is 3 in these problems. Instead of moving out 3 right on this rotated arm, we just use a negative R value, which indicates that we're hopping backwards. Remember, you want to keep landing on this original point right here. The whole point of this question is that all of your answers should be right here, but just they assume different names based on the kind of R value and the kind of rotation that you're using. Okay, so rotate 40 degrees, and instead of coming out on this arm, hop backwards. What makes you hop backwards is a negative R value. So that would be a third answer. So this is called, it was called in chapter 6, giving coterminal points. Now they're just referring to it as 3 other pairs of polar coordinates, which all stand for 3, 140. They all represent the same exact location. Okay, in part B, we have a harder problem because they are giving it to you in rectangular form. Notice that there's no theta here. So in part B, you have been given negative 1, 1. And if you're going to be giving 2 pairs of polar coordinates for the point with rectangular coordinates negative 1, 1, we first need to convert from x and y to r and theta. Okay, so right now you have x, you have y. We want to know what this is as r and theta, because the directions say give 2 pairs of polar coordinates. Okay, so one of the formulas that you were given on subsequent pages was r squared is equal to x squared plus y squared. So r squared, we're on our way to getting r. Here is x squared. This is y squared. So we have this squared is 1, this squared is 1. We have r squared is equal to 2. And then if we want to know what r is, then we just simply take the square root. Take the square root here, take the square root there, and there is what our r value is, square root of 2. Okay, now they said I have to give 2 pairs of polar coordinates. I'm going to get the first one right now as soon as I figure out what theta is. So whenever you are using this formula right here, tan of the angle you're looking for is equal to y over x, you're really finding just the reference angle any time the point is not in quadrant 1. If you were in quadrant 1 with these 2 coordinates, then your actual theta would be the same as the reference angle. So you go directly to the actual theta. But for any point that is not in quadrant 1, and this is not in quadrant 1, when you're at negative, positive, you're in quadrant 2. Okay, so anything in quad 2, quad 3, or quad 4, you're finding the reference angle first, and then you're going to find the theta that's related to it. Okay, so here we go. We're going to do tan of the reference angle. The y value is 1. This is -1. So you have this. You have tan of the reference angle is equal to -1. And you can get your calculator to help you with this, or you might just know it. The only time you can possibly get a tan value of 1 or -1 is if you're in a 45-degree triangle. So your calculator will at least get you the reference angle. Just switch these two. Got to put it in inverse form if you want your calculator to tell you what the angle is. So it's tan of the number is equal to inverse tan of the number. You just bring the number over here and the angle over here when you want to go from non-inverse form to inverse form. Remember, your calculator is going to give you an angle, but it is only the reference angle. Therefore, no matter what your calculator gives you, you will turn it into a positive angle. Reference angles are always positive. So let's look right here. And let's make sure that our calculator is in degrees, because we're not going to recognize what our calculator is offering us unless we're in degrees. So we are good. Quit. And then we're going to do second inverse tan of -1. See, it tells us 40. It says -45, but just reference angles are always positive. So just 45 degrees. I'm going to put a little note about that so you can continue to work on that. Always positive for your reference angle. Okay. Now what we're going to do is we're going to take that knowledge that the reference angle is 45 degrees and we're going to get ourselves in the proper quadrant. Remember, even with this r and theta that we're trying to come up with, it still must be in the same quadrant as the x and the y. So you know that -1, 1 is in quad 2. Think about it. If this was your quad system right here, -1, +1, you'd be in this quadrant right here. So you better be in that quadrant when you start talking about the real theta. This reference angle is just a vehicle by which you get the actual real theta. Okay, get yourself rotated over, get yourself in the proper quadrant. And I'll be more specific, in the same quad as the original point, -1, 1, which is quad 2. We are trying to figure out what the real theta is, but that's all about the reference angle. Helps you get the real theta. Okay, so right here, all we know right now, because our calculator gave us this, is that the reference angle, which is always that little angle between the rotated arm and the x-axis. Well, if that's 45 degrees, where is this rotated arm? Because where the rotated arm is the actual theta. Always related to the reference angle. Okay, very much try to draw out anything that you are doing. You're taking a math course that is very, very geometrically oriented. And if all you can do is press things into the calculator, you do not know what you're doing. You will not be able to explain it, and you will not be able to understand it to the extent where you'll be able to show work, and therefore you will lose massive points. So make sure that you are, just as the lectures demonstrate, drawing everything so that you can bring a geometrical understanding to the trig that you are doing. Okay, so this is my reference angle. I got myself in the same quad as this -1, 1, and I now want to proclaim what theta is, the actual theta. Well, how many degrees have you rotated if you stopped 45 degrees before you got to the 180 mark? you're at 135 degrees. And that's what the real theta is. And a lot of students struggle throughout the whole course to understand the difference between reference angle and the real theta. When in fact, when everything is said and done, you go to take that final exam, most of the problems have to do with that, an understanding of the difference between the reference angle and the real theta. So we want to keep working on solidifying our understanding of that. Okay, so theta is 135. So here's one polar point. R is square root of 2, and this is the theta is 135 degrees. So they said that we have to give two answers here. And I do want you to understand that this could be also given as 3 pi over 4. I'm not going to go over how to convert from degrees into pi form because you've been doing that for 4 chapters now, so I'm going to assume that you can do that. But if you have questions, you can let me know in class. All right, so I think we got to give one more answer here. So how about if we just do the simplest of all things, and if we were standing on this point right here, where we were, square root of 2 is, just so you get an idea of what it is, not that we need to get a decimal version of it or anything, but I'll just mention it, that square root of 2 is 1.4. So instead of moving out 2 notches on here, you just say this represents square root of 2, 135. That's what you're representing right there. Square root of 2, 135. And if you want to get a real easy second answer, you could just stand right here at square root of 2, 135, and just rotate an additional 360. So this will be one answer, and this will be a second answer. So square root of 2 for that R value again, and then rotate yourself an additional 360. I'm going to give this in degrees. 135 plus 360. You could always, you could always convert it to pi form, radian form if you want. So 495 degrees will make you land in the same exact spot as the original. Therefore, both of these represent the same location. Okay. So moving on now to example 3. Find rectangular coordinates for the point given in polar coordinates. So you have an R and you have a theta here. Grab another pencil. Find rectangular coordinates. So x is equal to R cosine theta. Okay, let's just kind of remind ourselves what's going on at pi over 2. This is the pi over 2 location, also known as 90 degrees. And right at this location, if you're on a unit circle, x is 0 and y is 1. X is 0 right here and y is 1. Remember that the x is the cosine and the y is the sine. So in these formulas, x would be the R value, which is 3, cosine of theta, 0. And then y would be the formula R sine theta. So that would be 3 times the sine value right here at pi over 2, which would be 1. Okay, so the x value was 0 and the y value was 3. This is x and y, whereas this one was R and theta. Okay, moving to example 4. Find the rectangular coordinates once again for the given point in polar coordinates. This is our R, this is our theta. Okay, so we're going to rotate to 135 degrees. Recognize what that rotation of 135 leaves us with respect to reference angle. Okay, if this was 135 and this is 180 and we never made it to 180, that means this rotating arm stopped 45 degrees before it got to 180, because 135 plus 45 is 180. So it stopped that many degrees before you got there. Close up that triangle, back right into special right triangles where both legs are square root of 2 over 2. But because of the quadrant you're in, and the fact that the horizontal leg represents x or cosine, it is negative, while this represents y, or in other words, the sine value, and y values are positive here. Okay, so when we go to do x, rectangular coordinates mean they're looking for x and y. Okay, so x is the formula r cosine theta, which in this case the r was 9, and we wanted the cosine at 135, which just means rotate to 135, recognize the reference angle, and with that reference angle you have an angle inside your right triangle, which tells you what the legs are. Okay, so the cosine is the horizontal leg, the negative square root of 2 over 2. This 9 is the same thing as 9 times 1, so it's numerator times numerator. I'll float that negative out front over a denominator of 2. That's x. Y, on the other hand, basically same thing, only positive. So it goes by this formula right here. Our value is 9, and then it's sine of 135, but this triangle that we've drawn based on a rotation of 135 gives us both cosine and sine. They're just the legs on the triangle, and the legs are determined by the reference angle. This is the main theta. This is called the reference angle, that little angle that's inside your triangle with its vertex at the origin is the reference angle. So sine is the positive square root of 2 over 2. So it's 9 square root of 2 over 2. That's your y, and then you can collect them together and report them as a point. Notice that this answer that I'm giving, anything where you have a negative x and a positive y, negative x, positive y, if you're thinking the xy system, is going to be in quad 2. Just like when I plotted this r theta, I'm in quad 2. Let's put it up here. Okay, always make sure that they coincide like that they agree with each other with respect to this xy answer that you're getting and the r theta that they started you with. Both of these were in quad 2. Okay, moving to example 5. It says this time that rectangular coordinates of a point are given. You want to find r and theta this time. So this time it is x and y that you already have, and you want to go and find r and theta. We're going back the other way this time. So r squared is equal to x squared plus y squared. That was one of the formulas we got on the first page. And so r squared is equal to 2 squared plus negative 2 square roots of 3 squared. Just following the formula to get our r value. Okay, so this is going to be 4. When we square this coefficient out here, which would give you 4. Squaring that means negative 2 times negative 2, which is 4. And then when you square this, it just makes the square root come off, and out comes the 3. So this squared would be 12. So it's a 16 here and r squared here. We want r, so we have to take square root here and square root here. So this is r is equal to 4. We can only use the positive value, not plus or minus here, because it represents the hypotenuse, and that can't be negative. Okay, so we have our r value, and now we're going to get theta. Now remember, this theta better be in the quad that is suggested by positive x, negative y. Think about that. If you went positive x, negative y, you would be down here somewhere in quad 4. So when you give your theta, you better also be in quad 4. Okay, this is where you have positive x's and negative y's. Keep that in mind. So here we go. Because we are not in quad 1, anytime you're in quad 2, quad 3, or quad 4, this tan formula is only getting you the reference angle to begin with. You're not getting the actual theta until after you get the reference angle. So we're going to start here. Y over x, well, here's your y right here, the negative 2 square roots of 3. And your x is 2. These 2's cancel, leaving you with negative square root of 3. You can get your calculator to help with that. It's going to be, and you remember just how to write it as an inverse. When you want your calculator to find an angle, you just go inverse and switch these two. Put the value here that you want the angle for, and the angle goes over and hops over into its place. Okay, so we're going to go second, inverse tan. I am in degrees, and I'm going to put in there negative square root of 3, close it up. And it gives me negative 60 degrees. Okay, so negative 60 degrees would be down, rotating this arm down 60 degrees, which means still that the reference angle is 60 degrees. Okay, even though your calculator gives you that negative, it's really just trying to give you the reference angle. Okay, so that reference angle is 60 degrees. Now let's look at the directions that are being given for this particular problem, because they can change up the directions on you, and you have to, know what you're being asked for. So if you're being asked for an angle that's between negative 2 pi and positive 2 pi, that means that they're allowing you to rotate negatively when you go and report your theta. So if you want to indicate that you're down here in quadrant 4, you want to indicate the direction in which you rotated. So yes, this reference angle might be 60, but your actual theta, also signifying which way you rotated, is negative 60. And I only know that you can give this answer because of the way that the instructions are given. They want you to give a positive R value, that's what greater than 0 means, but you can give a theta that's between negative 2 pi and 2 pi, which means this is okay to give this particular answer. Sometimes they'll tell you to give a positive theta. They'll indicate in the instructions to give a positive direction angle. Okay, so the R here is 4 and negative 60. And, just look and check for a second that if you were to plot this point right here, rotate to negative 60 and then move 4 units out, you'd be in quad 4, just like the original X and Y. Okay, let's move to the next one. Give me 1 minute. Okay, so, and then, you know, I want to give these answers in radian form too, just so you don't lose that skill. So this is the answer in degree form, and if you want to give it in radian form, what's equivalent to 60 degrees, if you want to just convert it, is pi over 3. 180 divided by 3 is the same thing as 60. It is negative. Okay, so this is in degree form, radian form. Okay, number 6. Rectangular coordinates are given. You can give a negative angle based on these instructions. They want you to give a positive r value. So let's do r first. So r squared is equal to x squared plus y squared. So r squared is equal to negative 4 square roots of 3 squared. That's your x. Plus your y value is this right here. So that's equal to, let's see, if I was to square that out there, that would be negative 4 times negative 4, 16 times, if I square that portion, the square root comes out comes the 3, so that would be 16 times 3 is 48. And then if I was to square this, I would get another 16, 48 plus 16. 64. Okay, all of this is on the right side of the equation. So it's r squared is equal to 64. I really want r, so I'm going to take square root here, square root here, and I get r is equal to 8. Okay, then moving on from here, I want to do, let's do my work on here. I want to do the angle. So let's do that next. Now notice that right here, if you were to plot negative, negative, you're down here. You're in this quad right here. Quad 3. So by the time everything is said and done, your r and your theta better be in quad 3 because that's where negatives are. And the x and the y is both negative. Okay, so now let's see. Any quad other than quad 1, find the reference angle first. Using the same definition, y over x. So it's tan of the reference angle is equal to y over x. Okay, this is going to cancel. This time you're getting 1 over square root of 3. And you can leave it like that because you're just going to be putting that in the calculator anyway, so your calculator can help you out with the reference angle. So you know how to get an angle from your calculator. Just rewrite it as the inverse. And all you have to do to rewrite it from non-inverse form to inverse form is switch these two. Bring that value right up against the trig function and let the angle jump over and take its place. It is the reference angle we're finding first. And that's because anytime you're not in quad 1, you must find the reference angle first, then the actual theta. Okay, so let's get the calculator to help us. We're still in degrees here. Because if you were doing it in, keeping it in radian form, you wouldn't recognize. You could always just take your degrees and convert it to pi form if that's what they want as the final answer. So second, inverse tan, and then I'm going to have, whoops, 1 divided by, I wanted to calculate that square root of 3 first, so I'm going to put an extra pair of parentheses around it. I know that you need to, but I'm going to. Okay, so this is just me doing the denominator. We can try it without the extra pair of parentheses to see if it's okay. So this is going to give me 30 for my reference angle. Let's see if we get it without these extra parentheses. So second, 1 divided by second function, square root of 3. Yep, you do. So you don't need the extra pair. Okay, so 30 degrees. Reference angle is 30 degrees. Now remember, We want to be in quad 3. So if I am in quad 3, let me rotate over to quad 3. Now I'm going to actually go for the real theta. Okay, so here we go. Using the information that my calculator just gave me, here I am in quad 3. Reference angle is 30 degrees. I'm going to give a positive angle this time. I mean, if I was down here in quad 4, I would just rotate negatively to get there in the fastest manner possible. But here, you're all the way over here, so I'm just going to rotate positively until I get to where this arm is in the third quadrant. So if you were at 180, and then all of a sudden you rotated to 180 plus an extra 30, because that 30 is the reference angle, you'd be at 210. Another name for 210, well, think of this as pi over 6. 180 divided by 6 is the same thing as 30 degrees. So you can also think of that reference angle in radian form. And if that was the case, you'd want to think of this landmark of 180 in radian form so that you could give a final theta not only in degrees, but also in radian form. So this landmark, 180, same thing as 1 pi. What's another way to write 1? 6 over 6. Why would I bother to use 6's? Because the reference angle has a denominator of 6. Let me write it over here. Okay, if your reference angle has a denominator of 6, you want to think about how to name this landmark 180, but in pi form, how to say 1 pi in terms of 6's. Just any number over itself is 1. Okay, so what does that make the theta in terms of radians? Well, you'd be at 6 6's plus 1 extra 6. So this is the name, the pi form of 210 degrees. So you can give that answer as 8, 7 pi over 6 if you're giving it in radians, or you can give it in degrees if that's what they're allowing you to do. You just have to read the directions and see what they want. But they are most infatuated with radian form in my math lab, or in most of the softwares that you're going to be using to do your homework and quizzes and so forth. Okay, so moving to example 7. The letters x and y represent rectangular coordinates. Write the given equation using polar coordinates. Okay, so what we have in this particular problem is, let's see. Okay, so for x, we have this definition, r cosine theta. And then for y, we're trying to move into polar form now. Write the given equation in polar form. We have this definition, r sine of theta. So I can replace x with its polar equivalent. I can replace y with its polar equivalent. And then if I want to try and solve for r, what I can do in this particular problem is just factor out the r. I could factor out the r, and this would be cosine of theta minus sine of theta, if I factor out that common factor. And then I would just give an answer in terms of r. By dividing this expression right off of the r, I'll be able to isolate the r and give an equation for r. So I'm dividing this side by cosine of theta minus sine of theta, and so I'm going to have to divide by that same expression on the other side. So cosine of theta minus sine of theta. And then that's my final answer. And this is how you would get your equation if you were going to put it in your graphing calculator. You would just solve for r, and then you would put your calculator in polar form, which we'll do later in the chapter. And all of the y is equal to keys will switch over as soon as you put your calculator in polar form. They'll all switch over to r's, and you go and feed your equation in, and you get a polar graph. Okay, next we have 3x squared plus 3y squared is equal to 2. And in this particular problem, again, same thing. We're going to plug in this for x, r cosine of theta for x that we're seeing here, because they want us to move into polar language based on these directions, and we'll use this for y, r sine theta. So it's 3r cosine theta squared, according to this equation, plus 3 r sine of theta squared again is equal to 2. Okay, so this is going to be 3. We're going to square the r as well as the cosine. So r squared cosine squared. And then here we're going to have 3. Again, r squared sine squared is equal to 2. Then at that point, you want to try to at least isolate the r term, whether it's in its r form or r squared form, but let's take out the common factors here. So let's see, what can we do here? We can take out 3 and an r squared. That is common to this term as well as this one. And then there would be 3r squared times what would give you this first term back, cosine squared, plus 3r squared times what would give you this second term back, and that would be sine squared. Then we have something that's equivalent, which could actually, very much simplify the situation that we're in right now. And that is the equivalent of cosine squared plus sine squared is 1. That's from chapter 1. Well, not chapter 1, excuse me, your first chapter is chapter 6. I think in 6.2, they were giving you these Pythagorean identities. Cosine squared plus sine squared is equal to 1. So at this point, we have 3r squared. 3r squared times 1 is 3r squared is equal to 2. And then you're just going to give your final answer as either r or r squared, whatever degree the particular problem has. So I'm going to at least divide off this 3, and there we go. I have an equation where I've isolated the r term. There's no other items over there where the r or the r squared is in this particular problem, and that is the polar equivalent of this equation. And by the way, when you do get into the sections where you are graphing these things, you're going to see that it is much harder to graph when it's in XY form because you have to solve for y, and that takes a lot of steps. Whereas to put it in this form is not as hard. So sometimes polar lends itself much more easily to actually getting the graph. You get the same graph whether you do it this way or this way. It's a circle. Okay, so now moving on to example 9. In number 9, we have x squared is equal to 18y. So in this particular problem, we're going to use exactly what we've been using for x each time, which is r cosine theta. And then we're going to square it because this is x, but this says x squared. And then we're going to go 18 times y. Y is the same thing as r sine theta. Remember, those definitions are right up here at the top of the page, and they were given on the first page of this section outline. X is r cosine of theta, y is r sine theta, and that's what I've been using for each one of these problems. So it's r squared cosine squared theta, and then this one is just 18r sine theta. So We have an r squared term and an r term, so about the best that we can do here is just to at least get everything on one side. We're not going to be able to isolate the r, so we can at least give the answer like this: r squared cosine squared, and bring this r term over here as well. And we can just give the answer like that. Okay, so we've zeroed out the right side, brought all r terms. I mean, you can't isolate for r because you have a square term and a linear term. So we'll leave it just like that. All right, now let's see. Can we do anything else to this that might simplify it a little bit? Okay, one thing, let's see. Nope, I think that's about as good as we could get for that one. All right, let's go to 18x times y. And here we're going to start off with 18, plugging in once again for x, r cosine theta, as we have for the last 4 problems and in many of the problems in this section, and for y, r sine of theta, equal to 1. Here we would have 18, r times r would be r squared, and then we would have cosine of theta, sine of theta. Now, whether you're going to note it, I don't know if they will mark this wrong, but you could actually simplify this further, because you could take part of this 18. I see a formula happening right here. I can create the double angle formula for sine. I don't really know if you remember this. It was either in 7.1, 7.2. Actually, it was in chapter 7 somewhere. It might have been actually 7.6. But I think there was double angle formulas in that section, and there was this formula. The sine of a double angle is 2 times the sine of theta times cosine of theta. That was the double angle formula for sine. 2 sine of theta, cosine of theta. And I can get that to happen here, so I think I'm going to, instead of reporting my answer with 2 trig words, I'm going to simplify it by using this double angle formula here. First, let me make this look like this. Okay, I'm going to leave 9 as the coefficient of the r squared, and I'm going to be thinking about this as 2 times 9. From that 18, I'm going to leave the 9 in front of the r squared, and I'm going to bring the 2 right in there. And right there, I could replace all of that with sine of a double angle. 2 times cosine of theta times sine of theta is sine of a double angle. So at least I don't have 2 trig words in there. And that's a lot of what you did in chapter 7. You took more complicated identities and simplified them by knowing what's equivalent to what. Very tough chapter because there's a lot of identities to memorize. That was one of them. Double angle formula for sine, which is what this is here as soon as I moved the 2 in front of it. So now if I did want to report this answer, this would be fine to just leave the answer like this. 9r squared times sine of 2 theta is equal to 1. And this is the polar equivalent of this rectangular equation. Okay, moving to example 11, which is actually the last example. And we're going to complete the general form of the equation using rectangular coordinates. So in this particular problem, let's see. What can I do here? I think what I'm going to do is try and create something right in here where I can plug an x. Remember, I'm trying to get into rectangular coordinates, so I would love to be able to plug in, I need to be able to plug in x's and y's for the expressions that I'm seeing here. Now, instead of squaring both sides, because if you square this side, you're going to get 100 cosine squared. Instead of squaring so that you get an r squared, try doing this. That'll give you an r squared, for which you will then be able to plug in the rectangular equivalent, which is x squared plus y squared. So that'll give you a way to get rid of this, any ideas of polarism introduced by the r. If you're going to multiply this side by r, you need to multiply this side by r. So now you got r squared on the left. I'm going to wedge this r right in here so you'll see it, that this is 10 times r cosine of theta. But we've been saying throughout this entire section that r cosine of theta is nothing more than x. That's one of the formulas that we have used repeatedly in this section, as well as this formula. How to relate polar type values to rectangular motions. Same thing here. This is just how to relate rectangular to polar. So once I do that, I can come right in here and replace that r cosine theta with its equivalent. So I'm getting rid of any kind of notions that suggest polarism, like theta and r. And I'm getting rid of any notions of polarism here by getting rid of r squared. I'm replacing it with x squared plus y squared. Okay, at that point, let's see, you have, and I think I would just bring everything to one side. They're probably going to want, require you to give the answer that way. That would be x squared. If you bring this over here, it'll be negative 10x. Sometimes they ask you to complete the square, and you'll just have to see if they want you to go any further. Completing the square can be done whenever you have either the x or the y family and you have a second degree term as well as a first degree term. But I believe they're going to let you leave it like this. That would be more in a section where they're asking you for the center of the conic section. Because these shapes that are being suggested in this section, and also we'll go into it more in section 9.2. They're ellipses, they're hyperbolas, they are, parabolas, and those things have either a vertex or a center. And the reason we learn to complete the square for any family where you have a second and a first degree term is so that you can find the vertex, so that you can find the center. That's the whole, one of the main purposes for completing the square. However, you're not being asked for that information here. You're just being asked to take this polar equation into rectangular form. That's what you're being asked for, so you can leave it like this. Okay, that completes section 9.1.